Have you ever wondered why diamond is extremely hard while glass breaks easily, or why table salt forms perfect cube-shaped crystals? The answer lies in something called a crystalline solid. Today, I'll introduce what crystalline solids are, their characteristics, and why they are important in chemistry. A solid is an atom, molecules, or ions that are arranged closely together and regularly in a complete order. Most solid substances are crystalline, and the arrangement of particles maximizes the total force of attraction between them. These forces can be ionic, covalent, hydrogen bonds, or van der Waals forces. There are four types of crystalline solids, including metallic solids that consist of metal cations surrounded by a sea of delocalized electrons, ionic solids that consist of positive and negative ions held together by strong electrostatic forces, covalent network solids that are composed of atoms connected by covalent bonds in a continuous network, and molecular solids that consist of neutral molecules held together by intermolecular forces. There are various properties of crystalline solids. One of them is that they have an ordered structure where their atoms are arranged in a repeating pattern, forming a crystal lattice. These solids have a sharp melting point as they exhibit a distinct melting point where they transition from solid to liquid. Furthermore, crystalline solids are anisotropic, meaning that they can vary with direction due to the specific arrangement of particles. Last but not least, they have a definite heat fusion. This means that a fixed amount of heat is needed to melt crystalline solids.
So next, there are three objectives included in our video presentation, which are to learn about what crystalline solids are and how atoms, molecules, or ions are arranged in an orderly crystal lattice. Secondly, to discuss the key properties of crystalline solids, including their ordered structure, melting point, anisotropic nature, and definite heat of fusion. Lastly, to demonstrate the importance of crystalline solids in chemistry by relating their atomic structure to their physical properties and real-life applications.
Assalamualaikum, I am Arlene Dania and I will be presenting about the three metallic crystal structures. The first one is the body-centered cubic, BCC, where it has a coordination number of 8. The unit cell consists of 2 atoms, 8 at each of the corner, which is multiplied by 1 over 8, which equals to 1 whole atom. Another 1 whole atom in the center, making it a total of 2 atoms. Next is the face-centered cubic, FCC. It has a coordination number of 12. This unit cell consists of 4 atoms, 8 at the corner multiplied by 1 over 8, which equals to 1 whole atom, same as the BCC structure. But what makes it different is that FCC also has 6 halves of atoms at each face of the unit, which equals to 3 whole atoms, making it a total of 4 atoms. Last but not least is the hexagonal closed pack HCP. It has a coordination number of 12. This unit cell consists of 6 atoms, where there are 12 at each corner, which is multiplied by 1 over 6 that equals to 2 whole atoms, and 2 halves of atoms at the top and bottom center of the unit equals to 1 whole atom, and another 3 atoms at the center of the unit, making it a total of 2 plus 1 plus 3 is 6. Crystal defect is defined as the imperfections in the arrangement of constituent particles in solids. The ideal crystal simply does not exist because all solid contains defects in it. There are 2 types of crystal defects, which are stoichiometry defects and non-stoichiometry defect. Stoichiometry defect is the imperfections from ideal arrangement of constituent particles in an atom. The ratio of cations and anions remains the same. There are 4 types of this defect, and they are vacancy, Schottky, interstitial, and Frenkel defect. Non-stoichiometry defect is the presence of constituent particles, which makes ratio of cation and anion to be different. There are 2 types of this defect, and they are metal excess and metal deficiency. Vacancy defect is where an atom is missing from its regular site. This is due to sufficiently high temperature. Some atoms have enough power to lift their energy. This causes the density of the substance to decrease. Meanwhile, Schottky defect happens when an equal number of cation and anion are missing from their regular sites. This is to maintain the electrical neutrality of ionic compounds. Hence, the density of substance also decreases. Interstitial defects is where an atom occupies an empty space between the regular lattice site of crystal. The addition of atom causes the density to increase. Finally, Frankel defect is when an ion leaves its regular site to an interstitial site. The density of the substance does not change as no atom leaves the solid.
What are the differences between diamond and graphite? Diamond composed of single-element carbon atoms arranged in 3D network. Each of these carbon atoms covalently bonded to 4 other carbons in a tetrahedral arrangement by strong covalent bonding. Diamond does not conduct electricity because there is no free-moving electron to conduct electricity. Furthermore, diamond has a very strong covalent bond, has high melting point of 3550 degrees Celsius and is very hard. In daily lives, diamond is often used in cutting tools and grinding.
So in graphite, every carbon atom is bonded to 3 other carbon atoms by covalent bonds. It exists in hexagonal layer structure. Free electrons move continuously within the entire layer of graphite. Thus, it is a good conductor of electricity. Graphite is black, soft, brittle, and slippery. In daily lives, graphite commonly used in lubricant, batteries, and pencils. So, to conclude, crystalline solids are materials arranged in a highly ordered and repeating crystal lattice. This regular arrangement gives them unique properties. For metallic crystals, the 3 common crystal structures differ in their coordination numbers and the number of atoms in each unit cell, which influence their physical properties. Understanding the structure and properties of crystalline solids is essential because it helps explain the behavior of many materials and support their applications in fields such as engineering, electronics, construction, and material science.